The least squares problem is formulated in terms of a minimum. So let's think about the optimality conditions. At what value of its argument is a function minimized? Let's start talking about differentiable functions of one variable. So f is a function mapping real numbers to real numbers. There's a graph of f, for instance. If f achieves a minimum value at some x equal x bar, then it must be that the derivative of f is equal to 0 at x equal x bar. So having a minimum at x bar implies that the derivative at x bar equals 0. But the derivative also equals 0 at inflection points, maximums, and other minimums, which raises the possibility of local minimums, such as here, and global minimums, perhaps, over here. What we conclude here is that if f has a minimum at x bar, then indeed the derivative is equal to 0 at x bar. But anywhere that the derivative is equal to 0 does not necessarily correspond to a minimum, at least for general functions f, as we've drawn. How about for functions of many variables? Let's have a differentiable function that maps n variables to one variable. We'll draw some graphs momentarily with MATLAB. Suppose this achieves a minimum value at some x bar. Now take any direction d, define a scalar function gd, notice it only maps r to r, as follows. G sub d at t is f at x bar plus td. So at t equals 0, gd is just f of x bar. But as t deviates from 0, then the argument to f deviates from x bar along a single direction d. Notice that t is a scalar. T moves the n-dimensional variable away from x bar, but in the direction defined by d. Now if f has a minimum at x equal x bar, then it must be that the derivative of g at t equals 0 must be 0. In words, I'll say that a minimum at x bar implies that the derivative at x bar equals 0 in every direction. Here's a picture depicting the math that we laid out. On the left is the graph of a function of two variables. x1 and x2 are in the horizontal plane, and f of x is on the vertical axis. This function achieves a minimum at approximately x1 equal to 0.75 and x2 equal to negative 0.5. You can see the minimum there marked. Think of that as x bar. Passing through x bar are a series of one-dimensional lines. Those represent x bar plus td for different directions d, with t ranging from negative to positive, causing the line to start on one side of x bar, and then at t equals 0 pass through x bar, and then for t greater than 0 move through along a straight line defined by the direction d. The black lines in the surface are the value of the function along those lines. The black lines represent f of x bar plus td, and the blue lines represent x bar plus td. As a function only of t, the parameter that's moving us along those blue lines, the graph of the functions are shown on the left. That really is g sub d of t versus t. Notice that since the function is at a minimum at x bar, the one-dimensional slices all have a slope of 0 at t equals 0 over here. That's precisely what the math says on the left. If x bar is a minimum, then for any line in the x1, x2 space passing through x bar, the slope of the one-dimensional function defined along that line will be 0 at t equals 0. T equals 0 corresponds to being right at x bar along one of these one-dimensional lines. Let's visualize this in MATLAB. The first example will be exactly as was depicted in the slides. X bar is at the minimum, and we'll see that all the one-dimensional slices have a slope of 0 at t equals 0. Here's the first line. On the surface, the black lines appear, and then over on the right is simply g of d as a function of t. Notice at t equals 0, the slope is 0. Let's try a different direction. The value on the surface is shown. The one-dimensional slice of that is now shown on the right. Not much different than what we had just seen. A new direction in the surface, a one-dimensional plot. Another new direction in the surface and along the one-dimensional plot, and so on. What's common about all these, since x bar was at the minimum, is that the slope in the one-dimensional lines is always equal to 0 at t equals 0. That's evident here. In this example, x bar has been moved off the minimum. You can see where I've chosen x bar, where the vertical line pierces the x1, x2 plane. It's not at the minimum. Let's draw a line through there and now graph it in the surface, and the one-dimensional projection looks like that. The slope is not 0 at t equals 0. Let's pass through a different direction. Another line in the surface. Its value agrees at t equals 0. Again, the slope is not 0. Let's do a few more lines. Notice that for all the one-dimensional lines, they all have exactly the same value at t equals 0. That's because at t equals 0, they're all passing through x bar. But generally, there's nothing special about the slope at t equals 0. In some cases, the slope is positive. In some cases, the slope is negative. It clearly indicates, though, that the point chosen, x bar, is not a minimum, because for all of the directions, there's a better choice than t equals 0 to achieve a lower value than the value achieved at t equals 0. Hence, x bar is not a minimum.